Hi, nice to see you. Good afternoon, everyone.
Good afternoon.
So today we start a new topic. Good afternoon. That will be interference of electromagnetic waves, and we will discuss which conditions are necessary to observe interference for light, and what are reasons for that, which type of interference effects we can observe, and how we can quantify, like start our the process of quantifying this effect. So let me first share with you my screen. I need to also our slides. Okay. So due to electromagnetic like wave nature of light, we can observe such effect, which characteristic of waves, as interference. So what is interference? It's superposition of two or more waves, which due to this superposition create certain pattern of waves, which we call the result of interference. So in example, we can consider interference of light, like two-slit interference, which is actually shown here on the slide. And as a result, on this viewing screen, so-called, we will see a pattern, interference pattern, which is repeating bright and dark lines. So it means we will have large light intensity and low light intensity, actually going from maximum to minimum. So such repeating pattern is the result of interference of two waves, which are emitted from source one, like slit one, and slit two. So obviously we don't observe such pictures in everyday life, and there is a reason, like there are several reasons for that, because we need special conditions for this interference to happen. First of all, the light itself should be monochromatic, means it should consist of a single wavelength, electromagnetic wave. Light originated from like what we experience everyday conditions. It's either natural light from the sun, or light from light bulbs, or some other like LEDs, LED devices. This is continuous spectrum of many different wavelengths, and that's why we obviously don't observe interference effects when we have such broad spectrum light. We need to send it through a device which is called monochromator, so it can cut all other wavelengths and transmit only one wavelength. Or we can use a laser, which is already a source of monochromatic light. So then we need these two slits and their diameter should be very small. It should be smaller than the comparable, let's say, to the wavelengths, because we need to consider this as point source of electromagnetic wave. So in order to have not just light pass through them and move straight as we considered in geometrical optics, but we should observe some diffraction effects. So this light would spread in different directions, and also in those areas where it should not be if it follows geometric optics rules. So that's why these two slits should be very, very small. So they should serve as sources of so-called coherent monochromatic illumination. Monochromatic, it comes from the origin that the light before the slits is monochromatic, but coherent means that at any moment of time, there is constant phase shift between these two signals which we receive between which we receive from this source 1 and source 2. So that is a list of requirements which can eventually lead us to such interference effect, and will help to do such measurement and then try to understand what's going on there. So as we said, there's a wavelength, means the frequency also the same, the wavelength is the same, the frequency is the same. And when we observe superposition of these two wavelengths at some point, let's say some point P, so we already see, but we will quantify it in more details, that the path light has to travel from slit number 1 to this point will be different from the path it should travel from slit number 2. Depending on the so-called path difference, we will either observe so-called constructive interference when we see enhancement of light intensity, means we have these bright lines, or destructive interference when we observe just no signal, dark lines. So here on this image, we can learn a bit more in details about this interference from two slits. There is some distance d between two slits, and distance L from the slits to the observing, viewing screen. Now let us consider some point P on this screen, which position with respect to this horizontal line which goes through the middle distance between the slits is defined by angle theta. So that is angular position of point P, defined by angle theta. So now if we consider this yellow triangular, here we also have angle theta, we see that the signal, the electromagnetic wave, which travels from S1 to P, marked as distance R1, is smaller than R2, and the difference, this delta, is defined by d, distance between the slits, which serves as hypotenuse for this right angle triangular, times sinus theta. So this distance difference or path difference is actually the key parameter here, which defines how these two coherent waves will interact with each other at this given position of point P, and which type of interference we will observe. So let me stop sharing this for a moment so we can write here. If this path difference delta is equal to 0 or some integer multiple of wavelengths, so then we will have the case when two waves will arrive at this point P in the same phase. Means that they will enhance each other, and eventually we will get higher light intensity, like this constructive interference effect at the this point P. So this condition we can write as follows. So it will be d times sinus theta, which stands for this delta, should be equal to m times lambda. And this m is some integer multiple, like 0, starting we go from either 0, or it will be 1, 2, 3, and so on. So if this condition is satisfied, because of this path difference, waves will come in phase and constructive interference will be observed. Let us now come back again for a moment to our slide. So obviously, if we come back here, if we pick up this point O, which stays on the horizontal line, which goes through the middle point between the slits, the path of two waves will be the same. So that will be so-called like first main maximum of the interference. And then depends, if we go further, it just depends on the angle. We get constructive or destructive. So we have condition for constructive interference. Now let us write also condition for destructive interference. So in this case, this path difference delta should be some odd multiple of lambda divided by 2. So in this case, we can write the following. Let's write here bright. So that is condition for constructive interference. And here we can write d sinus theta dark equal to m plus 1/2 times lambda, where m also changes from 0, 1, 2, 3, and so on. So that is the case when two waves will arrive in this point at angle position theta dark in opposite phases. And since they possess the same amplitude, they will completely cancel each other, and we will have just dark fringe. So the linear position of these fringes along the screen can be related with angular position. So from this image. Let me share it again. So we have L distance from the slits to the screen. Here is this horizontal line which goes through the middle point between two slits. And if we want to define linear position of point P, which is Y, and relate with theta, so we go for tangent theta is equal to Y divided by L. So that we can write tangent theta is equal to Y divided by L, where Y is linear coordinate, linear position of observing point on this viewing screen. So we can express from here linear positions for bright and dark fringes. Y bright will be equal to L times tangent theta bright, and Y dark will be equal to L times tangent theta dark. Now, if we consider small angles, in that case, there is not a big difference between tangent theta and sinus theta. So we can assume at quite high level of accuracy that tangent theta is approximately equal to sinus theta. And with this, we can again give definitions for the linear position of bright and dark fringes. So in this case, we can write Y bright position will be equal to L times already sinus theta bright. And we know that from this relationship for bright angular position, we can express it as L, distance between slits to the viewing screen, times M times lambda divided by D, which is the distance between the slits. Similar, Y dark will be L times sinus theta dark, and that should be from this relationship, should give us L times M plus 1/2 times lambda divided by D. So now we have quantitative description for angular and linear positions of bright and dark fringes. So far, we were discussing only position of the central part of this bright and dark fringes. However, light intensity distribution is not sharp. So it goes to maximum in the middle, and then it starts to decrease. So let me share again my screen. You can see here that we have the brightest point in the middle, where the maximum of light intensity, and then it gradually decreases, going to minimum somewhere in the middle of this dark fringe. It's not some step function, some square shape. is some gradual increase of light intensity and decrease. So at this point, we already can tell the position of this maximum of bright fringes and minimum for dark fringes, which gives us which is determined by conditions for constructive and destructive interference. However, it is necessary also to learn about this light intensity distribution, and that's what we will try to do now. So it's like next step of quantitative analysis for interference pattern. Let me stop share. And the most reasonable approach for this, since we know that light intensity is proportional to electric field square of electromagnetic wave, the most reasonable approach here will be to consider two waves, in particular, how electric field is changing over time. So we can write for electric field for wave 1 will be equal to E naught, some maximum value, times sinus omega t. At the same time, we have another wave, E2, which has the same amplitude, sinus omega t, but it possesses some phase shift with respect to the first one. So, which obviously is directly related with, with the path difference. So we remember that path difference is R2 minus R1. That is equal to D times sinus theta. And if this delta is equal to lambda, to the wavelength, then we can write that phi is equal to 2 pi radian. So taking this into account, we can write that the path difference of delta is the same fraction of wavelengths as the phase difference phi is the same fraction of 2 pi. So we can write this ratio delta divided by lambda is equal to phi divided by 2 pi. From here, phi is equal to 2 pi divided by lambda times delta. So we know that delta is d times sinus theta. So we can write 2 pi divided by lambda times d sinus theta. So that is the expression for this phase shift between second and first waves. Now, when we want to get the interference condition for these two waves, what is interference? It's superposition. So we need to add these two signals. So resultant electric field will be equal to the sum of E1 plus E2. And that will be E naught times sinus omega t plus sinus omega t plus phi. So that is our resultant electric field, which will be created by interference of two waves with electric field E1 and E2. Now, using the following trigonometric identity, which looks like this: sinus A plus sinus B can be represented as 2 sinus A plus B divided by 2 times cosinus A minus B divided by 2. So taking this into account, we can modify the previous expression for the resultant electric field. Assuming that A is equal to omega t plus phi, let's say, and B is equal to omega t. So in this case, this resultant electric field can be expressed as 2 times E naught times cosinus phi divided by 2 times sinus omega t plus phi divided by 2. So the amplitude now for the resultant electric field, which is formed due to interference of two waves, will be that part which is without time dependence. So that is like prefactor here before sinus. So that will be amplitude value 2 epsilon naught times cosinus of phi divided by 2. So at, and we see that this amplitude is actually what we are looking for, because here we get just time dependence of electromagnetic signal, but what we actually observe on the screen, that's the intensity, like the magnitude of this amplitude of electromagnetic, of electric field, because we remember intensity is proportional to electric field squared. So now we can see that at phi phase difference 0, 2 pi, 4 pi, and so on, the amplitude will be maximum, and that will be 2 times E naught, because cosines will get to be equal to unity. At phase difference pi, 3 pi, 5 pi, so on, the amplitude of this signal will be equal to 0, because cosinus will be equal to 0 too. So we already have this trend for electric field, but again, intensity of light and electromagnetic wave is proportional to E squared. So let us, and most of devices, actually also human eye and other detecting equipment, like detectors of light, they operate with some integrated, some average light intensity over some time. So we always deal with some exposure. So in this case, we can proceed taking into account that I is proportional to E squared, and E squared will be equal to 4 times E naught square times cosinus square P divided by 2 times sinus square omega T plus P divided by 2. Since we care about some average, because detectors which can kind of see or detect these positions of like distribution of light intensity on the viewing screen, they operate with some average light intensity. So we need to get average, and from previous discussions we already remember that average of sinus square is omega t over one period of electromagnetic wave. On average, that gives us 1/2 for one period. But we can consider either from one average for one period or average for many periods, doesn't matter. It will give us 1/2. So in this case, taking this into account, we can write that intensity of lighting, which is formed on the viewing screen, will be equal to I maximum, some amplitude intensity, times cosinus square of phi divided by 2. So what really matters is this phase shift between two waves, and then angular dependence of light intensity will look like this equation. So here we go from electric field. We don't have explicit equation for intensity, but since we know that average over time will be 1/2, and then there will be necessary to add another parameters to go from here, from this part, to I maximum. So we don't go for that. We don't care, because what we we want to see not in absolute magnitude light intensity expressed, but just to express in some arbitrary units for light intensity, while this light intensity will be distributed over the viewing screen. So that will be the expression for light intensity as a function of angular position of every point at the viewing screen. However, at this form, it's still not clear how it really related to the angular position or linear position on the screen. So for that purpose, we need to recall how we expressed this phase difference, phi. Previously, we did that for this phase difference. Let me check here. Yes, it's 2 pi divided by this equation. 2 pi divided by lambda times d times sinus theta. And theta is already angular position of this point. So here, let me write it down here. It will be 2 pi divided by lambda times d times sinus theta. Now we can substitute it in this expression for light intensity distribution. So it will be I equal to I maximum cosinus square. This will be pi times d times sinus theta divided by lambda. So that is already equation for light intensity distribution as a result of interference of two waves along viewing screen in terms of points position, like angular position of points on this viewing screen, and for small angles, you remember that tangent theta is approximately equal to sinus theta, and that could be expressed as the ratio of y, linear position of point, divided by L, distance from the slits to the screen. So now we can substitute this sinus theta with y divided by L, assuming that we do not go from this horizontal line, which goes through the middle of the middle distance between the slits too far. So the angle theta is small. In that case, we can also express intensity of this interference distribution, intensity of light distribution after interference of two waves as follows. It will be cosine square pi times d divided by lambda L, and here we have y, linear position. So we have two equations which give us angular and linear distribution. In both cases, we see that we have this cosine square function, which is some periodic function with minimum, which possible is 0. And then we go to, when it reaches unity, we go to maximum light intensity. So here we can see this. So that is the pattern of light intensity distribution along this viewing screen. We have a periodic function which goes through 0 light intensity to some maximum which corresponds to this I maximum, what was in our equation. So as a result, that's what we observe on this viewing screen. And if we have some very small photodiode which detects light intensity as a function of position, we would see that this is how light intensity increases and decreases. So definitely there is no like sharp step functions. However, sometimes we want to get such sharp, let's say, maximum brightness, and then step function, so it goes maximum, like saturated here, and then abruptly it goes to 0. For that purpose, we need to use multiple slits interference, and that's how this picture for interference with different number of slits looks like. So we go from 2 slits, which we consider. So we have this cosinus square function, quite gradual distribution of light intensity. So when we increase number of slits, then we get some minor maximums, like secondary maximum. We have primary maximum, which are the same positions as previous maximums. And we get some secondary maximum, which are much, much lower in intensity. As we increase further number of slits, the number of this secondary maximum and their intensity will drop. So there will be more of this secondary maxima, and their light intensity will be smaller. So in the contrast, light intensity of the main peaks, primary maximum, will remain the same, their maximum value, but they will become narrower because some of this space will be occupied already by secondary maximum. If we increase it further, we get conditions when we have plenty of secondary maxima, very narrow primary maxima with the same as initially light intensity. And then on the background of this very small secondary maximum, this will appear as very sharp, narrow fringes of interference, which indeed we have, if we know position of this maximum, which coincides with position of maximum, and for like constructive interference, in the case of just two slits, their angular and linear positions will be the same, but just very slight deviation from this position, and you see already how abruptly light intensity changes, not so gradually as in the case of two. So we will get very abrupt edges of this constructive interference maximum. So that's how the pattern of interference can be modified if we use large number of slits. Obviously, those distributions for light intensities will become much more complicated from the point of view of analytical analysis. That's why we learn how light intensity will be distributed for interference just for two slits. And also the position of this maximum and minimum, as you see from here, it will be exactly like position of the absolute maximum. This will be the same for all cases of two or multiple slits. So if you have any questions, you're welcome. Like summarizing, we introduced a new topic, which is interference of electromagnetic waves, of light in particular. We discussed which conditions are necessary to get interference effect. Means we need monochromatic light. We need very small slits, which dimension should be comparable to the wavelengths, and some coherent two electromagnetic waves which originated from these two slits. Coherent means that the phase shift between them will remain constant over time. So this phase shift is directly related to path difference, which two electromagnetic waves travel from the slits to the point of observation on the viewing screen. And we quantified under which conditions we will have constructive and destructive interference, providing angular and linear positions for this maximum and minimum of interference. And also after considering that, we describe the distribution of light intensity along the viewing screen, highlighting that we have maximum and minimum, but between maximum and minimum of this interference, light intensity profile doesn't change abruptly, so it gradually decreases and then increases. So we got equation which describes this angular and linear position dependence of light intensity. And if we want to get sharper interference fringes, like maximum fringes, then we need to gradually increase number of slits that will help us at the same angular or linear positions of maxima, make them much narrower, and then it will look like more like some step function where we have maximum and then just with a little bit of deviation in any direction, it will abruptly go to almost zero background. It will not be zero, it will be defined as this secondary maximum, but their light intensity becomes very small when we increase number of slits for this interference. So we will continue our discussion with considering other options for observing interference. It's definitely not only one option to create interference of light with using these two slits. So it's one of the experiments which is very straightforward in terms of understanding and quantitative description. However, there are other systems and conditions when we can see interference, and that is our topic of discussion for next time. Thank you very much for attention and have a good evening. See you on Wednesday.
Goodbye.
Bye.
Thank you for the lecture.
Bye-bye. Take care.